Hey everyone, let's go over the solutions for this week's section worksheet. The topic for this week is on search. In the first problem, we're given a small state space graph, shown here. And we're asked to run 5 different search algorithms. We want to see what the order of states expanded are, and what the paths returned by each of the search algorithms are. Let's first go over some small details. For all of the following questions, we'll be running graph search, which means in addition to a fringe, we'll need to keep track of a closed set of states expanded. Also, we may run into ties in our search. So for example, for depth first search, we may have 2 paths that are tied for the deepest depth. To handle such ties, in practice, it doesn't really matter which of the candidates we choose. But in order for us to avoid multiple possible solutions for the worksheet, we're going to have to define a tie-breaking scheme that works as follows. We'll line up all the tied paths starting from S and stride in columns from left to right. When we hit a column with the mismatched state, we'll take the path that has the earliest letter in the alphabet. So let's illustrate this with an example. Let's consider 2 paths SAB and SAC. So the earliest mismatch happens in the 3rd column here. B comes before C in the alphabet, so we'll choose SAB. Let's do one more example. Consider the paths S to B to A and S to A to Z. So the earliest mismatch happens in the 2nd column here. If we compare B and A comes first in the alphabet, so we'll actually choose this path, SAZ. Okay, let's begin with depth first search. We'll start off by having a fringe that just contains the path S and a close set that is initially empty. We'll pop S off the fringe because that's all we have right now, and we'll push S's successors onto the fringe, which in this case is S2A, S2B, and S2D. Okay, good. And S will go into the closed set. So, now depth first search will go for the deepest path. Well, since all the paths are of depth 1, we'll break ties alphabetically. So here we have A, B, and D. A comes first in the alphabet, so we'll choose S to A. We'll put A onto the closed set, and we'll look at what S to A successors are. Well, S to A has 2 successors. S to A to C, and S to A to S. I'm only going to put S to A to C onto the fringe, and not even consider putting S to A to S on the fringe. Why is that the case? Well, even if we put SAS on the fringe, and end up considering to expand SAS, we're actually never going to expand it because S here is already in the closed set. Okay, so to save myself some time and space, I won't write down these paths that I know will never be expanded again. Okay, so we have S to B, S to D, and S to A to C left on the fringe. Well, S to A to C is deepest, so let's expand that next. We'll put C onto the closed set and look at its successors. So the successors of SAC are S to A to C to D, and S to A to C to G. Okay, so now we have a tie for the deepest path, which are the 2 we just put on. D comes before G in the alphabet, so we'll take off SACD, put D onto the closed set, and put this path's successors onto the fringe, which in this case is S to A to C to D to B, and S to A to C to D to G. Okay, now we have another tie for the deepest path, which are these 2 down here. And we have to break ties again, so in this case B comes before G, so we'll consider expanding SACDB, put B onto the closed set, and S to A to C to D to B's successors are SACDBS and SACDBD. However, since both S and D are already on the closed set, we're not going to expand either of these 2 paths ever again, So let's not even consider putting that on the fringe. Alright, so next off from this remaining fringe, we'll have S to A to C to D to G. Let's pop that off. This path actually satisfies the goal test. So we're done. So the expanded states are pretty much in the order of the closed set. So that's S, A, C, D, B. I'll put G for here. And the path returned is going to be this path that passed the goal test, which is S to A to C to D to G. Alright, moving on to breadth first search. So, like in DFS, we'll begin with a fringe that just contains the path S, and we'll also have a closed set that is initially empty. We'll start by popping off S from the fringe and putting S onto the closed set. S's successors are S to A, S to B, and S to D. Breadth first search prefers shallow paths, but the remaining 3 paths on the fringe are equally as shallow because they're all in depth 1. So we'll have to break ties. S to A is what we'll choose because A comes first in the alphabet. We'll put A on the closed set, and we'll look at what S to A's successors are. S to A successors are S to A to C and S to A to S, but I'm only going to put S to A to C on the fringe. Okay, so now which path or paths are most shallow? Well, we have S to B and S to D both of depth 1, so we need to break a tie here because those are our shallowest paths. B comes off next, so we'll put B on the closed set, expand S to B, its successors are S to B to D. S to D is the next shallowest path, so let's pop that off. We'll put D on the closed set and expand this. So its successors are S to D to C and S to D to G. Okay, so now we have 4 things left on the fringe. All of these paths are depth 2, so we have to break ties. The mismatch happens in this column here. So we'll start off by popping off S to A to C. Put C on the closed set and put its relevant successors back on the fringe. So that's S to A to C to G. And then the rest of the successors are blocked off by the closed set. Let's expand S to B to D next. Well, the terminal state here on this path is D. D is already in the closed set, so we're not going to expand this path. S to D to C. Similarly, C is already in the closed set, so we're done with that path. Then we have S to D to G. Well, that passes the goal test, so we're done. The expanded states are S, A, B, D, C, G, and the path returned is S to D to G. Alright, moving on to uniform cost search. So what's going to be slightly different from the previous 2 algorithms that we saw is that with UCS, we need to keep track of the total path cost for a given path. So in addition to keeping track of which path is on the fringe, we need to associate that with a number indicating the cost. So, as we usually start off with a fringe just containing the start state and the closed set, which is empty. Okay, so I guess we can put here that the backward cost of this path is 0, right? It takes 0 cost to get from the start to the start. So let's pop that off. Let's put S's successors on the fringe, which are S to A, S to B, and S to D. S goes in the closed set. Okay, so now what are the weights associated with these paths? Well, we have to look at the path cost. So for S to A, for example, we have the cost of this edge, which is 2. So let's put 2 here. S to B, the weight is 3. Let's put 3. And S to D, the weight is 5. Okay, good. So UCS will expand the path with the lowest path cost. In this case is S to A. Let's pop that off. Put A on the closed set. And put its successors onto the fringe. The relevant successor is S to A to C. The total path cost along S to A to C is this 2 here and this 4 here. So 2 plus 4 is 6. Okay, now let's see which path UCS will take next. This S to B has the lowest cost of 3. So let's put B on the closed set and expand S to B. Well, S to B's successor is S to B to D. This has a total path cost of 3 plus 4, which is equal to 7. Okay, so what is cheapest now? Well, that's S to D. Let's put D on the closed set and expand S to D. So we'll put S to D to C with cost of 5 plus 1. That's 6. And S to D to G, which has a path cost of 5 plus 5, which is 10. Okay, so now what's cheapest? Well, we have a two-way tie, SAC and SDC, both of which cost 6. So we break ties. This A here comes before this D, so we'll choose SAC. Let's put C on the closed set, and let's expand SAC. So that the relevant successor that we need to put here is SACG. This has a total path cost of 2 plus 4 plus 2. And that adds up to 8. Okay, good. So these 4 paths are left on the fringe. S to D to C is the cheapest, but C is already in the closed set. So let's take that off and not expand that. S to B to D is next cheapest, but this D is already in the closed set. So similarly, we don't need to expand that. Then we have this path that costs 8. Let's pop this off. Hey, here's the goal test, so we're done. The expanded states are S, A, B, D, C, G, and we get that from here. And the path is S to A to C to G. Alright, so far we've seen examples of uninformed search algorithms that did not make use of these heuristic values at each state. We're going to move on to the informed search algorithms which will make use of these heuristic values. So let's start off with greedy search. What greedy search will do is it prefers paths where the last state of the path has a very low heuristic value, because the heuristic value is an indicator of how far you are away from the goal, and if the value is low, that means you're pretty close to, hopefully pretty close to a goal. So that should be in the direction of which we should go. So let's start off again with the fringe that just contains the path S, and a closed set that is empty. We will pop S off the fringe and enqueue its successors S to A, S to B, S to D. And the value we want to put for these paths is the heuristic value at the last state. So let's see, what's the heuristic value at A? Well, that's 2. That's right here. What's the heuristic value of B? That's 5 here. And the heuristic value of D, that's here. That's 1. So the path with the lowest heuristic value is S to D. Now, let's put S on the closed set. So let's expand S to D. We'll put D on the closed set and enqueue S to D successors, which are S to D to B. The heuristic value of B is 5. S to D to C. The heuristic value of C is 2. And S to D to G. So the goal has an implicit heuristic value of 0. So let's put 0 here. Alright, so which of these paths remaining on the fringe has the lowest heuristic value? So that would be S to D to G. We'll pop that off the fringe. This path passes the goal test because this path ends in G, so we're done. The expanded states we can tell from the closed set it's S to D, and then we'll put G here. And then the path returned is S to D to G. Alright, the moment you've all been waiting for, A star search. So what A star is it's just a combination of uniform cost search and greedy search. What uniform cost search has to offer is the backward cost. Remember, that's the sum of all the edge costs along the path. And what greedy search has to offer is the heuristic value at the last state along the path. So that gives you the future prediction on how far you are away from the goal. And we'll set that equal to this f cost value, and this is the number we want to associate with the path on A star. Okay, great. So let's begin with the fringe with just the start state and a closed set that is empty. We will pop off S from the fringe. Note that it doesn't really matter what number we associate with S because it's always first to go off. We'll put S on the closed set, and then we'll enqueue its successors S to A, S to B, and S to D on the fringe. Okay, so let's look at what the costs are along these paths. For S to A, the G cost is the edge cost here. That's 2. So I'll put a 2 here with the G on top. The heuristic value is the heuristic value at A. That's also 2. So let's put a 2 with the H on top here. And that means that the F cost is 4. Similarly, the G cost for S to B, that's 3. And the H cost is the heuristic at B, so that's 5. Means a total cost of 8. For S to D, the G cost here is 5, and the heuristic at D is 1, so the F cost here is 6. Okay, great. So A star prefers low F cost paths, so we'll take S to A because this is the lowest F cost we have. We'll put A on the closed set, and we'll enqueue the relevant successors of S to A, which is S to A to C. The G cost on this path is the cost to get to A from start, that's 2, plus the cost of getting from A to C, that's 4. So in total, that's 6. And the heuristic value is going to be for C, that's 2. So we put a 2 here. The total F cost is 6 plus 2, which is 8. Okay, so now the lowest F cost is S to D with the F cost of 6. Let's put D on the closed set, and let's look at this S to D successors. Well, S to D successors are S to D to B, S to D to C, and S to D to G. S to D to B has a G cost of 5 to get to D plus 4 to get to B. So that's 9. And the heuristic value is for the last state only, and the heuristic value of B is 5. So let's put that, and the F cost is 14. So for S to D to C, the G cost is 5 to get to D, and then 1 to get to C, so that's 6. And the heuristic value is for the last state here, which is C, so the heuristic value is 2. That gives us a F cost of 8. And lastly, S to D to G has a path cost of 5 plus 5, that's 10. The heuristic of a goal is implicitly 0, as mentioned in greedy search. So the F cost is 10. Okay, great. So now which path has the lowest F cost? Well, we have a three-way tie, S to B, S to A to C, and S to D to C. So we need to break ties. We'll break ties alphabetically, so let's put them aligned like this. This is the column of mismatches here, this BAD column. A comes first in the alphabet, so we'll choose S to A to C to expand next. Let's expand S to A to C, put C on the closed set, and enqueue the relevant successors here. That's just S to A to C to G. And the G cost for this is 2 to get to A, 4 to get to C, and 2 to get to the goal. So in total, that's 8. The heuristic at the goal is 0. So the F cost along this path is 8. We again have another three-way tie for a f cost of 8, which is the cheapest, and that's S and B, S to B, S to D to C, and S to A to C to G. Well, this column is mismatched. Again, A comes first, so we need to pop off this path. This path ends with a goal state, so we're done. Let's see where I can write this. The expanded states is going to be S, A, D, C, G. I remember this part comes from here. And the path returned is S to A to C to G. Okay, let's go on to question 2. In this question, we're asked to define a state space for the classic Towers of Hanoi problem. Just to quickly go over this problem, there's 3 different pegs shown here, and n different disks, so that's here. Each of these disks are of a different size. We'll start with the start configuration in this picture, where all of the disks are stacked in the leftmost peg, and they're sorted from largest to smallest size. And the goal is to move all of these disks to the rightmost peg, again sorted from largest to smallest. For your moves, you can only move one disk at a time, so you can take one of these disks on top and move it to another peg, but there's a constraint that the disk that you move has to be smaller than the disks that are existing on the peg. So you have to keep everything in sorted order from largest to smallest. Okay, so let's start by thinking about a state space. There's quite a few variety of possible answers here, but let's first think about what kind of information we need. Recall that our state representation should be minimal and must encode information to help us define the start state, the successor function, and the goal test. So the most important information here is which set of disks does each peg contain. A similar statement to this is which peg does each disk lie on. And how will we be able to get that constraint that disks on top have to be smaller than the ones below it? Maybe we can try labeling the disks from 1 to n in increasing size, and then keeping track of sorted lists for each peg. Maybe that's one option. Let's actually try that. So our proposal is this. Let's label the disks from 1 to n in order of increasing size. We'll maintain 3 different ordered lists, one for each peg, and the elements inside the list correspond to which disk, so the disk index that we just labeled, that the peg has. So let's see if this works. So for our start state, well, we want sort of this configuration here. So that's pretty simple. We'll have 3 lists. The middle peg and the right peg have no disks, so they're empty lists. And the leftmost peg has all the disks, so that's 1 to n. Okay, so this will be our start state. Our goal test is also very straightforward because we just need to check if our state is equal to kind of a mirror image of this. So that's 2 empty lists here and all the disks sorted in order in the rightmost peg. So that's this here. Okay, the successor function is also pretty straightforward because it derives itself based on the rules of the Towers of Hanoi problem. So let's put that here. We can pop the first integer off the list, push it to another list, so long as it's smaller than the first element in the list being pushed to. That's exactly saying the same thing as you can take off one of these disks from a peg, move it to another peg, such that it's still the smallest one so it's being stacked on things that are larger than it. Okay, so that's just a restatement of this. Let's move on to the state space size. The state space size is the total number of states that could be possible with our state representation. So in order to see this, let's think about how many ways we can put n different items into 3 collections. because that's exactly what we're doing. We have n disks and we have 3 different pegs. Well, let's take this element here that can go in any of these 3. So we have 3 choices for the first one. For the second guy, we also have 3 choices. So that's going to be multiplied with the previous choice here because we're looking for combinations. And so forth, right? So 3 times ... times 3. And we do this n times. That gives us 3 to the n. Let's see if this 3 to the n number is feasible with n equals 2. So we're considering the case where n is 2. We claim that there are 3 to the n states. So with n equals 2, that's 3 to the 2 states, which is 9. We do have 9 different states here, and these are actually the only 9 states that you can get. So the answer here will be 3 to the n.